Hello and welcome to this eighth week in the eighth TA session for the TA session for week 8 for the course of Physics of Materials, which is an NPTEL course for the year 2025. The course instructor is Professor Pratap Haridas from IIT-M, and my name is Mohammad Tahsin. I'll be the TA for this course. Okay. As usual, let's start with a brief recap of the things that we discussed last week. So in the previous week, that's week 7, we discussed the so we have been following our discussion from Maxwell-Boltzmann statistics onto the Fermi-Dirac distributions, and we have been considering uh, the need of having a different kind of statistics which arise from the need for which arises from the limitations of the Maxwell-Boltzmann statistics, right? So we saw that when we use the Maxwell-Boltzmann statistics, we overpredict the values of some quantities and underpredict some others. And to account for these discrepancies in the model, we have to consider the Fermi-Dirac distributions and treat the particles, that's the electrons, as quantum particles rather than as classical particles, right? And when we make these changes, incorporate these changes into our model, uh, our aim is that we should be able to address the discrepancies of the Maxwell-Boltzmann statistics. That's the aim for now. And in that pursuit, we have discussed the Fermi-Dirac distributions. So if I just show you the diagram that we obtained in the session prior to that, we saw that the distributions look like this. So on the y-axis here, we have the probability of occupancy of energy levels, which are designated by EI, and on the x-axis here we have the energy levels EI, right? And then we at 0 Kelvin, we see that all the energy levels prior to the energy level EF, which is the Fermi energy, all energy including and lesser than the Fermi energy level, are fully occupied at 0 Kelvin, right? And then as the temperature increases, we see that the energy levels which are close to this Fermi level, only these energy of the electrons, the fermions present in these energy levels, they interact with or they respond to this change of temperature, and not all the electrons respond to the change in temperature as predicted by the Maxwell-Boltzmann statistics. So, but the in this distribution or this trend that we see here, we only get partial information. In what I mean by that is we do not know what is the number of allowed states or number of occupied states corresponding to some energy level EI. Right? This graph just gives us someone is trying to join. So this plot just tells us about the probability of occupancy of an energy level and not the entire information, right? So in the last week we discussed the effect of the concept of anisotropy, right? And this is something that is experienced in a number of materials and in a number of properties. For example, in wood, we may experience anisotropy in mechanical behavior. In graphite, we experience anisotropy in terms of its thermal conductivity, right? And as well as electronic conductivity. So yeah, so there are some more examples that, for example, concrete, it's weak in tension and it's really strong in compression, right? So the concept of anisotropy, it arises from the way the material is structured up, right from its atomic distributions. So the way the atoms and molecules of a particular, so if we talk about metals, then the atoms of that metal, how they are distributed in space, that determines uh, the properties that they show along different directions, right? And so it depends on the crystal structure. And if we have a polycrystalline sample, so mostly if we take a piece of metal, most likely it will be in its polycrystalline state, right? It requires a specific method to come up with a single crystal of some metal, right? So in a polycrystalline sample, these uh, uh, let's say these properties along different directions, they balance each other, right? So if we have very large number of grains, then we would expect that there is some other grain which is exactly opposite to this grain, right? And that assumption works only if there are a lot of grains present in the sample, right? Then there would be some grain somewhere in the sample which would uh, exactly nullify, or in a way uh, uh, the properties there would be exactly as the inverse of the properties here, right? The orientations will be fully opposite to each other and the effects will balance out. So that happens in a polycrystalline sample with a large number of grains. But if we have lesser number of grains, then we may see these anisotropic effect, right? And if we are talking about a material model, then it should a good material model should take into account the uh, uh, let's say the properties, not just the properties. It should take into account the anisotropy, or it should be able to predict why there is anisotropy in the materials along different directions, right? So the way we incorporate this information into our models is by assuming a periodic potential which varies in different directions. Okay, for example, we took the example of this kind of a distribution. uh, it's okay, so we have these oblique distribution of uh, okay, let's look at these positive ions, which have each contributed, let's say, one electron, shown by this uh, solid dot. And if we look at the structure that these ions are packed in, we see that this is the unit cell of this structure, right? And here we can see that the distance between the ions in this direction is different than the distance between the ions in this direction. And this difference in packaging of a material, it causes a variation in the potential that is experienced by these electrons moving around the ions in the form of a C, right? So since they experience different potentials along different directions, that accounts to the differences in properties that we measure across these directions, right? And so far what we had been looking at is that in all the models prior to this, we assumed that the potential throughout the uh, throughout the conductor or throughout the sample is constant, right? So these free electrons, they move around the sample without feeling any potential, okay? But that's not the correct situation. The real situation inside a conductor or inside a sample is more complicated, and there are actually these ions which have so if an electron is around very close to an ion, then it would feel greater attraction as compared to if it's at any other location, okay? So an electron, if we take an electron, it experiences this kind of a potential force, okay, in the conductor, right? So near the ions, so these black dots represent the ions or the cores, positive cores. There the potential of energy of the electron is very low, like highly negative, right, as compared to some other location. And we observe that this is the potential energy distribution of a single electron as it moves through the positive core of these ions. And we can approximate this kind of a potential by taking square wells, right? Because the analysis gets easier, and it will not cause any change of qualitative change in behavior, right? An electron which is experiencing this kind of a potential landscape, it would experience the same effects here as well, but the quantities might change. But we are more interested in qualitative behaviors, right? So if we take an example, so this would be an approximation of the potential well as experienced by an electron, and we see that there are two different levels of confinement that are happening here, right? One of the confinement is happening just around these ionic cores, where the length scale is very small, okay? And electrons present inside this energy well, they are called tightly bound electrons. These are the electrons which remain bound to the ionic core and do not move in the sample like the free electrons do, right? And then we have another level of confinement which is called as nearly free electrons, right? And this is another level of confinement, but these electrons, they are free to move around the conductor, and they will be limited by the size of the conductor, their motion, okay? And there is some energy level which is represented in this pink color here, okay? And this is the highest energy level occupied by an electron when we start filling electrons at 0 Kelvin, right? The highest energy level filled by these electrons is called the Fermi energy, and it lies somewhere in this region, in the almost free electron zone, right, for metals. Now we see that there is confinement happening here at two levels, two different length scales. Then we made a couple of remarks which come from a very quantum mechanical perspective, which is that confinement leads to quantization of energy, okay? And what it means is, we took the example of a string to explain this. If we have a free string, it can take any number of undulations on any length scale, right? Because its one end is free. As compared to this one, if we take another situation where a string is confined between two ends, in that case there must always be a node here and a node here, okay? And due to these boundary conditions, due to this confinement, there are still infinite number of positions or infinite number of configurations that this string can take, but they are all discrete, right? They are not continuous. And this discretization, this is what's called quantization, okay? Now what's the relation between a string and an electron, right? Because we were discussing electrons. The analogy is that if we consider these electrons as quantum mechanical particles, then we can describe them, we can ascribe a wave function to them and then describe their behavior using this wave function. And the wave function, the solutions of wave function can be imagined as a string tied between two points, and which is having some undulations, because that's how a wave behaves, right? So this wave-like behavior, if an electron is confined to move in a certain space, then its wave-like behavior gets quantized. In other words, its energy gets quantized, okay? It cannot have arbitrary wavelength or arbitrary wave number and so on. And we actually found a formula which says that this is how the wavelength and the number of let's say this is called a mode actually, but in quantum mechanical perspective we will call it a quantum number, principal quantum number. And this is actually the quantum number which can take only integer values, positive integer values. So this way the wavelength gets quantized, and consequently energy and frequency also get quantized, right? and we found an energy expression for energy in terms of the reduced Planck's constant, this h cross, which is equal to h by 2 pi. The k here, it's the wave vector corresponding to this de Broglie's wave with which the electron is moving. M is the mass of the electron. Okay. So, okay, finally, if we have this information of how energy is depending on the this wave vector k, we can solve a Schrodinger's equation for this system, right? So we imagine our system to be like this. It's confined to move in a space of 0 to a, and the potential is infinite here and infinite here, means it cannot leave this well, our particle. And once we write the Schrodinger's equation for this, because now we can assume that within this region, within 0 to a, the potential is constant. If it's constant, we can very easily assume it to be 0. It will not change the nature of the solution. Okay, and still, and when we solve this equation, we find that this wave number gets quantized, right? Similar to what we expected or what we observed in a string when we confined it into at two ends. And this n here, it's again the principal quantum number, and then we can find an expression for En, which is the energy of nth quantum state, right? And it has this expression here. And if we look at how it depends on n, or how it depends on k, there's a parabolic variation, right? So which can be shown by this parabolic behavior here. Here k is the wave vector, and it's quantized. Okay, this E will not have value, it will not be even defined for any arbitrary k. There are only fixed k's for which this E will be defined. That's why this parabolic trend is shown in a dotted manner. So the takeaway from this is that potential wells, electrons reside inside potential wells when they move inside a solid, and because they get confined in this potential well, we see the effects of quantization. Okay, that's the takeaway message from this. So now in today's lecture, what we would like to do is we would like to relate these effects to basically develop a theory which gives us an idea about the number of states or number of electrons present at a particular energy level. Because the trend that we saw earlier, that only gave us partial information, that only gave us the probability of occupancy of that energy level. It did not tell us anything about the number of electrons or the number of states present at that level, right? So that's where we are heading towards. Okay, so this is week 8. Let me write the name of the course. Okay, so this is week 8. It's supposed to be week 9 TA session today, but unfortunately due to some travel schedule, I could not conduct a session last week. So I'll put up a video on YouTube for week 9 sometime during this week, and then we will have our regular sessions on Saturdays as was the schedule originally, Okay? So there will be one extra video which will be posted on YouTube sometime this week before Saturday, and then we will have our regular session for week 10 that will be on Saturday 6 p.m. Okay, so this is week 8. Let me turn on lights. So today what we want to discuss is the topic which is called density of states. Okay. And what we mean by density of states is the number of electrons per unit volume present at a specific energy level at a particular temperature. Okay, so let me write it. Roughly, it means number of electrons per unit volume at a specific energy level. Right, at a given temperature. Right? But what is the use of this information, or why are we interested in finding this information? Because our ultimate goal is to, so we'll use this information because this is now we are developing the Drude-Sommerfeld model, right? We want to use this model to explain the incorrect predictions. No, actually let's see, we have already explained why the predictions made by the Drude model are incorrect, right? Because it predicts that all of the energy levels or all of the electrons will interact with the thermal field, right? So today what we want to do is we want to explain let's say, so we want to quantitatively describe the not the behavior or the contribution of electrons to the thermal conductivity. Okay, this is our goal. So we want to develop this information, right, to achieve this goal. Because if we recall from the Drude model, we saw that this quantity, right, what we call CVE there, electronic contribution to the specific heat of solids, right, this was off by a factor of 100, right, when we use the Drude model. So we want to develop new statistics or this Drude-Sommerfeld model now to explain this, explain the why we see this factor and can we correct it. Okay. Now, if we go back to the expression of energy that we had here in the last week's lecture. Okay, so this is the expression of energy, and I'm going to copy it and I'm going to develop things from here. Okay, so basically what does this mean? Just to recall, this m here is the mass of electron. Okay, a here is the level of confinement, okay, or the length scale of confinement, or the width of potential well, in whichever way you want to describe it. Okay, I'm going to call it length scale of confinement, and m is the mass of electron. Okay, because of confinement there is quantization, and quantization means energy levels are discrete, and En is a formula for those energy levels. Okay, so we also had an equivalent relationship in terms of k, right, which was h cross square k square over 2m, right? This was an equivalent relationship between the energy and the wave vector, and here k is the, let me write it, quantized de Broglie wave vector. Okay, so these two formulae are identical. En here, this n subscript n, it refers to, let's say this is n is 10, right? So then this will be the 10th fundamental mode of the string. Okay, sorry, 10th, 9th overtone in terms of string analogy, right? So it would be the wave function corresponding to quantum number 9, principal quantum number 9, 9th energy level. Okay, so now this analysis was done in one-dimensional space. But if we extend the same things to 3 dimensions, what we get is, so 3D extensions, right? This En would be equal to this would be equal to nx square plus ny square plus nz square, with the assumption that the confinement is same in all directions. Okay, this confinement A, it's same in all directions. For simplicity, let's assume that for now. And similarly, we can modify this expression, this one as well. Let me write it in terms of the wave vector. It will be h cross square by 2m kx square plus ky square plus kz square, right? So this is the expression of energy in quantum number state, quantum number space, the n space, right? Quantum number space. And this one, this space, we are representing this energy in terms of the components of the wave vector, right? This is called the wave vector space. Okay, and as we will later see that this is called reciprocal space, right? So now what does this tell us? Okay, now these are coordinates, right? Nx, ny, and nz. These are coordinates in a particular coordinate frame. Similarly, if we take the other frame, k frame, the wave number frame or the wave vector frame, there the components would be kx, ky, and kz. Okay, so these are two different coordinate systems. We can think of them like that. And now let's see what happens for a constant energy. If the energy is constant, this is Planck's constant, it's already a constant. The mass is not going to change. And if we see this confinement can change, but for a moment let's assume that this A is constant. Okay, and this pi is already a constant, pi square. So for a given value of energy, right, this sum is constant. Okay, so for a given energy, for a given value of energy, and this should be, this energy cannot be arbitrary. Okay, this energy has to be one of the allowed energies for the system. It cannot be an arbitrary energy. Now let's say that, actually we should add that for a given allowed value of energy, we see that this sum nx square plus ny square is equal to constant, right? And similarly, so this is for the quantum number space. I'll call it n space. Okay, and similarly for the wave vector space, kx square plus ky square plus kz square, this is a constant. Antho, can you please stop sharing your screen? Are you sharing your screen?
No, sir.
Okay, something.
Sir,
Yeah.
we're not allowed to share our screen.
Sorry, what?
Sir, actually, we're not allowed to.
Okay. Okay. Let me try to present. Let me try to present again. Just a moment. Can you see the screen now?
Yes, sir.
So, yeah, so we were discussing about these two equations, and what we said is for a constant value of energy, these the sum here and the sum here, that should be constant. Okay, and since we said that these are coordinates in n space and k space, okay, so these equations, they describe a circle in their respective spaces. Okay, and this constant, let me call it constant 1 and constant 2, they don't need to be equal. In fact, they won't be equal. Okay, but they will be both the shapes of these iso energy contours, they will be spheres. Okay, in their spaces. So the point here is, the takeaway is, constant, or let me write, surfaces of constant energy. Okay, surfaces of constant energy, and the word we use to describe them is isoenergy surfaces or isoenergetic surfaces or contours. okay, are or describe spheres in n space as well as k space. Okay, so that is the first point. These are surfaces. Okay, so remember that our goal is to find the density of spaces, right? Now there's one highest energy level, right, that is occupied at the 0 Kelvin temperature when we start filling the states at 0 Kelvin. The highest energy level is called the Fermi energy level, okay, and the surface corresponding to Fermi energy, right? That surface is called, I think it's called Fermi sphere, right? Yeah, Fermi surface. Okay, and we use this word actually for when we talk about the Fermi energy in k space. That sphere is called Fermi sphere or Fermi surface. Okay, and it will be a sphere. Fermi surface is a sphere, right? So now what is our goal? Our goal is to find the density of electrons at an energy level EI. Okay, let me call it density function. You can call it density function as well. Density function for electrons. Right? Given an energy level, I should be able to find out how many electrons there are at that energy level. That is my goal. And now, so I'm going to define a few terms here. Okay. So let's define and actually this one should come under the definition. This is 1. Okay. So this is the density function for allowed states. Now there will be two points to consider here. One is the allowed number of states. The second is the filled number of states. How many of those states are filled, right? In Maxwell-Boltzmann distribution, we did not have such concepts. There was only one concept, which was the number of states there. There was no allowed number of states. You could have any number of electrons or particles anywhere at any energy level, right? But that changes here for Fermi-Dirac distributions. Now you have two concepts here. One is allowed state, the other is filled state. Okay, and now I'm going to define my second thing, N of E. Actually, we can't define EI. Let me write D as a function of energy. Okay, and I'll say N of EI, or let me just call E as well. This is the density of occupied states. Okay, how many of these allowed states are occupied for a given energy? Okay, so these are two definitions, and then it's easy to say or easy to write that N of E, density of occupied states, it would be equal to F of E times D of E. Why? What is F of E here? It's the probability of occupancy. Okay, given an energy level E, what is the probability that that energy level is occupied? Right, that is given by this factor F of E, and this we already know from our previous discussions. This is the only factor we knew. Our goal is to find this and this, right? And sometimes we can also place a 2 here, okay, just to count the spins of electrons differently, but this is not important. This 2 here is not important. We can arrive at same results or similar results qualitatively without having this 2 there, right? So what it says is the density of occupied states is equal to the product of density of allowed states multiplied by the probability that those states are occupied. Okay, and this is very straightforward from the principles of probability. So now, so how do we find this, right? Or how do we find this? Because there are still 2 unknowns in this equation. Okay, and now we are going to consider the fact, so we are going to count the states. Okay, so how do we count the states? So let me go counting of states. Okay, so how do we count a state? Now we know that, let's say that this is some Fermi surface, right? And now I'm just going to talk about the situation at 0 Kelvin, where this is the highest energy level, right? There will be nothing outside it. No particles will be outside it, okay? And inside this Fermi surface now, there are going to be other energy states, something like this, and then there is going to be something like this, and so on. Right? And let me draw this one in black or red. So this is our Fermi energy. Okay. Now we know that. So if I call this Fermi energy EF, so what I want to count is total number of states, total number of allowed, right? Allowed states. From 0 energy, or let me call lowest possible energy, to EF. Okay, this is what I want to compute. So how do I do this? Right? So if I consider, so in a way I want to compute what are the number of energy levels, what are the number of allowed states, right? And how I can do that is if I consider this entire thing to be sphere, okay, something like a sphere, and then divide by, let's say, the volume of 1, okay, let's say I treat entire thing to be sphere and then I divide by the volume of this. Now in this diagram I have drawn them in a way that they look like they are of different areas, right? this area is different. The area of this annulus is different than area of this annulus. Now, I could have done what I could have done is I could have made this annulus of smaller diameter such that the area of this equal to area of this. In that case, if I take this full circle here, this final circle, and divide it by area of this annulus, I expect to get somewhere close to 3 in this case, or 4, or some integer number, right? So that would give me the number of states present in my system. Now, I agree that this image is not very intuitive to the actual situation that we are describing. It's not a one-to-one map, but something like this we are going to do. We are going to take the final outer surface, which is the Fermi surface, and up to the Fermi surface, we know that these energy levels are quantized, right? They are not continuous. So if it's quantized, that means if this is my outer surface, there will be one surface here, which will have lower energy than this Fermi surface, and then there will be energy level here and here, but it will not be continuous, right? So what I'm going to do is I'm going to take one of the energy, these jumps, okay, calculate what is the width of this, and divide this entire thing by the width of that. Okay, it will give me the number of such energy levels. Okay, that is the idea. So what we are going to do is we are going to take the volume occupied by the states in n space. Okay, I can do the same thing in k space as well, but I will stick to n space here, and I'm going to divide it by volume occupied by a single state in n space, right? And this will give me the number of allowed states. Allowed, not occupied. Okay, so how do I compute this? Now I know the shape of this Fermi sphere or the Fermi surface. It will be it's a sphere, it's a spherical shape. So the volume occupied by that would be given by the volume of the sphere, right? So that's what I'm going to do. Okay. Now, right? So this principle can work for any energy, right? Even if this is not the Fermi energy, still the same approach would work. But in that case, I would get the total number of allowed states between zero energy and that energy. Okay, so this approach will work for any general E. And if you take EF, then it will give you the total number of states, allowed states between zero and Fermi energy. And that's finally what we are headed towards. But here, this approach can work for any general E as well. So, so the volume, so what will be the volume of this outer sphere? It will be 4 by 3 pi times r cube. Okay, now where do I get the r, the radius of this sphere? Right? Where do I get radius squared? This is the radius squared, right? Because x square plus y square plus z square is equal to r square. That defines a sphere of radius r in the xyz coordinate system. So r square will be equal to sum of these squares. And 4 by 3 pi r cube That is the volume, right? So I expect something like r cube here. So r cube I can get from nx square plus ny square plus nz square, right? So this is r square, and then I'll do 3 by 2, right? This would be r cube divided by volume occupied by a single state. What is the volume occupied by single state? It will be 1, right? Because how is the volume defined in 3D? It will be dx dy dz. Okay, so if this is my nx, this is my ny, and this is my nz, it's something like this. Okay, in this space, so consider this for some x y z, consider this point here, this point here, and we will have, okay, it's a bit tricky to draw, maybe consider this point here, and we will have something like this. Now what will be, so this is some state. Okay, now if there is immediately next state, that would correspond to one increment here, because it can only take integer increments, right? I cannot go 0.1 to the next state. I can have an increment of 1 in this coordinate, 1 in this coordinate, 1 in this coordinate. So dx would be 1, dy would be 1, dz would be 1. So the volume occupied by that new state, it will be 1, right? So this volume occupied by a single state is 1. And one correction is there, that when we say that this is the volume of the sphere, then these coordinates are allowed to be negative, right? Because if we have a sphere around the origin, it will contain all the positive as well as negative points. But all our coordinates, because these are principal quantum numbers, they only take on positive integer values. So we will be restricted to 1 octant of that sphere. Okay, so I will have a factor of 1 by 8 here. Okay, and this now is the total number of allowed states from 0 to an energy level E. It will be equal to this. Okay, and if we simplify a little bit, see, for this entire expression I will write n square. Okay, nx square plus ny square plus nz square, that is equal to n square, and n square times 3 by 2, 2 and 2 will cut off and only 3 will remain. So this would be and here also we can do some simplification. It will be 2 by 3, I think so. No, it will be 1 by 6, right? So nt of E, total number of allowed states up to an energy level E, it will be equal to 1 by 6. Just a minute. So if we evaluate this expression, we'll get 1 by 6 pi n cube. Okay, so this is the total number of allowed states. And now from here we have to go to And we can actually do one thing, because we know that En, we have the formula for En, right? It's right here. It's right here. And we can use this formula to replace this N here. Okay? In this expression, for N, I'm going to substitute the value here. So let me just write the final expression. This would be equal to using this, okay, I'm going to just put it in another color, and this will be equal to 1 by 6 pi, and then N will be equal to 2ma square E divided by h cross square pi square times 3/2. Okay, and what we can do is we can take this E outside. We can just write it as this, just to show that it's an energy. It depends on E, and how it depends on E is it has this power relationship. Okay, so now this is the total number of allowed states. So if there is a density function, so it should be related to some density function d of E in such a way that this nt of E should be equal to integral from 0 to E, this thing, right? So there should exist a density function such that if we integrate it between the energy from 0 to E, it should give us this value here, right? And that will give us this d of E. This consideration will give us d of E. And if we differentiate the both sides, so d and d of E should be nt of E divided by dE. So how do we differentiate this right hand side? We can use the Leibniz rule. Okay, just look it up if you are not familiar how to differentiate under an integral sign, and this will just directly give you d of E. So basically what you do is you just take this function and put this value here and differentiate this value with respect to E. Then you do then you subtract the same thing with the lower limit. Okay, so something like this. So if we have 0 and then a, and this is f of x dx, and we have to differentiate it with respect to x, then this would be equal to f of a dA by dx minus, let's say this is some b, so it would be f of b dB by dx. Okay, and I have used the same thing here in this expression. Instead of a, I have E, so I'll have d of E times dE by dE is 1, and then B is 0, so this thing will be 0. Okay, so this is the formula we have. So what it tells us is that if we differentiate this total number of electrons, total number of allowed states with respect to the energy, we will get the density. Okay, so we just need to differentiate this term here. Okay, and if we write, again I'm going to write the expression finally. So this d of E will have expression d by dE of, let's just copy this whole thing, right? And now you know that only one quantity depends on energy, the rest of it is constant. So this d of E will be this constant term here, it will come here, and then instead of, how do we differentiate 3 by 2 power? It will be -1, this power -1, so it will be e power half, and this 3 by 2 will get multiplied. Okay, and this 3 and 3 would cancel, it would be 2, and then 2 and 2 is 4. So I'm just going to write this expression. Okay, so this is the expression for density of states, right? So what we have here is, what does this expression give us? Density of allowed states corresponding to an energy E. Energy level E. And what does that mean mathematically? It means the number of electrons, if we take the number of electrons between, okay, let me write N of E, between some energy level, let's say E0 to En or EF. Okay, what is the number of electrons between these two states? It will be given by integral of d of E with respect to the energy between these two energy levels. Okay, that is the physical meaning of this density. So it works in an integral formalism. Okay, and so one interesting thing here is, from this equation we see that the density of allowed states is a parabolic function of the energy. Okay, and also we earlier wrote that N of E, or okay, so for NT is representing the total number of states, okay, allowed states. N of E is representing filled states, okay, number of filled states which are filled. So we wrote that this is equal to 2 times F of E times dE, right? Now since we know this as well. Okay, now if we try to plot this d of E, we have said that it's a parabolic distribution, so it would look something like this. So here again, on x-axis I am plotting energy, on y-axis I am plotting d of E. So the probability distribution would look like this. Okay, it's parabolic equation, something like what f of x equal to root x would look like. And I know that f of E has this kind of a distribution. Okay, this is the probability of occupancy. We know it varies like this, where this is the Fermi energy, right? So if I have to evaluate this now, number of occupied states, I just have to take product of these two. Okay, product of these two graphs. So it's not hard to see what that product would look like. Product would be right. So this is what the product of these two functions would be like. This is N of E, this is again E, this would be EF, and this is at 0 Kelvin, right? And then we said that if we go above, if we raise the temperature, distribution changes like this. Something like this, right? And then this graph, okay, let me call it T1 or T2 greater than T1. Okay, so similarly here the same trends will be observed here. Okay, so we will have because we are just taking a product of the two functions. Right. Same here. In green we have T2, which is greater than T1. Right. So this accomplishes our first part of the goal, okay, which was to find an expression for the density of states, right? And then we had to use this density of states information to come up with an explanation that explains the trend of CVE, electronic contribution to specific heat. Okay, so let's go there now, and it's straightforward, it's not very difficult. Okay, yes. So let me just rewrite the equations that we derived above, okay, and then modify them slightly for a more generic situation. Okay, so NT of E, the total number of filled states at an energy level E, this is equal to 1/6 pi and then n cube. Okay, no, let me write it in terms of the mass. It is 2m a square 3/2 and e to the 3/2 divided by h cross square pi square. Okay, so this is the total number of allowed states. This is the density of states. It is 1/4 pi, and the same thing here, same term reappears here, and then energy should be 1/2 right? So if we look at this confinement term here, the length scale of confinement A, we have a term a square and then 3/2. So effectively we have a cube term here, right? And since if you recall, I said that we are assuming that this a we have the same confinement in all directions, right? So in this case, this is the volume of confinement, right? And now I can actually, for a generic system which does not have the same quantization, same confinement in all directions, we can simply write this as 1/6 pi, and I can write V here to take out this effect of A altogether, and all other things remain the same. Okay, it will be 2m by h cross square pi square 3/2 times E 3/2, right? And similarly for the density of states, right? This is the modification I want to do here. Take out the a square term and put in a volume term here. Okay, so that's fine. And the other thing, now since these expressions are generic, if I want to evaluate them at the Fermi energy, there is no problem. I can evaluate them at the Fermi energy. Now why I'm interested in Fermi energy? Because everything is happening about the Fermi energy, right? Temperature starts interacting at the Fermi energy. Other states do not get affected. So with these expressions now, what I want to do is, yeah, so I can define a volume density, right? Just take this V and divide it here. Okay, so I can define this term and I can define this term. So this would be number of allowed states up to an energy level EF, right, per unit volume. And this would be volumetric density function. Now this one, the second one, right? This is a volumetric density function. The density of states per unit volume, density of allowed states per unit volume. Okay, and I am going to call these so simply I am going to write, okay, for this I am not going to write anything, but this I am going to call dv of E. Okay, it is just a nomenclature. dv of EF, right? And this I am going to call NF. Okay, and what does this term now define? It is the total number of allowed states per unit volume up to the Fermi energy. Okay, total number of allowed states per unit volume up to the Fermi energy. Now up to the Fermi energy at 0 Kelvin we have all the states there, right? There is nothing at 0 Kelvin, there is not a single state above Fermi energy which is filled, right? So what this expression shows us, it's simply the number of states per unit volume, number of allowed states per unit volume, right? Because the probability of occupancy here is 1. Okay, so that's why I'm going to represent it by NF, and this is simply the volumetric density of particles, of electrons at 0 Kelvin, of course. Okay, and what about the second term? Okay, well, let's take a let me call this equation A, and let me call this equation B. Right, now if I divide, I'll divide B by A. Okay, what does that do if I divide B by A? So first, so we have to take this expression here and divide by this. Okay, so on left hand side we will have dv EF divided by n of F. It will be equal to, so we will see large cancellation here, right? The only thing which will survive is 2 by 3, I think. It will be 3 by 2. And 1 by EF. Yes, because we are dividing this by this, right? So it will be 3 by 2, not 2 by 3. Okay, and now what we can write is dV EF equal to 3 by 2 NF by EF. Okay, so this is now the expression that we have to understand what this means. Okay, so this is saying the density function of occupancy of electrons per unit volume is given by this expression. Okay, where EF is the Fermi energy and NF is the density, so basically number of electrons per unit volume. Okay, and now so let's consider an energy change. Let's consider an energy change. So roughly what we need to remember here is EF for a particular material system, right? EF is constant. So what this term here, what it relates is, it relates the distribution of electrons, right? Distribution of electrons to the density, to the total number of electrons, right? So this is related to the number of electrons, and this is related to distribution, right? How those electrons are distributed across the energy levels, right? So this expression, this relates these two quantities. Okay, now if we consider an energy change delta E, what happens when we consider an energy change delta E? So remember that earlier we derived a distribution when we were doing the Maxwell-Boltzmann statistics, or even the Fermi-Dirac statistics. We said we had expressions of this kind, right? E power minus times delta E by kBT, right? So what these expression tells us, that if this delta E is order of, or as long as this delta E is less than kBT, all those states will have a high probability of occurrence. Okay, and if this delta T is greater than kBT, then the probability will go lower and lower. Basically this exponent, as long as this exponent is very small, the probability will be high. Okay, so we can write it as in the following way, that as long as the modulus of delta E is comparable to kBT or is less than kBT, right, thermal fluctuations can cause excitation. Right? Excitations of the order of delta E. Right? Of the order of delta E. Right? So what it means is that if delta E is the change in energy, then so let's revisit this graph here. Okay, so what it says is that, so this is the situation at 0 Kelvin, right? Now all this graph, all this equation it says is that only the electrons which are kBT away from here, okay, which are kBT away from here, only those can get excited. Okay, so if our energy is of the order of kBT, then around the Fermi energy, around this region around the Fermi energy. Only these electrons can participate in the excitation process, right? Other electrons will not feel the effect of temperature. So now what we do is, we will set this delta E equal to kBT for now, okay, although it's proportional, but let's set it equal to kBT. Then the number of electrons present between between delta kBT present in the region the best way to write it is in this kBT neighborhood of Fermi energy. Right? So we want to find what is the number of electrons present in this region that are going to interact with the thermal field. Okay? And that will now be given by, because we know the density, dV of EF times kBT. Right? And this is per unit volume basis. Yeah. So this is per unit volume, right? In a unit volume, this is the number of electrons that will interact if the energy or if the temperature change is of the order of, if the temperature change causes an energy change of the order of kBT. Okay? So this is the number of electrons per unit volume present in the this kBT neighborhood of the Fermi energy. Okay, and now recall that from the classical theory, okay, from the kinetic theory of gases, that each electron can absorb an energy which is equal to 3 by 2 kBT. Right? This is the energy provided to each electron if we raise the energy of the system by kBT. Right? So then the total energy change is equal to number of electrons participating in this exchange process times the energy consumed by each electron, right? Is equal to times 3 by 2 k by t, 3 by 2 kBT, right? So if we evaluate this, and let me call it E total, some total energy change, right? It will be equal to 3 by 2. So first I'll write the expression for this, dVEF, okay? So it will be 3 by 2 NF by EF. Then we have a kBT. Actually we have k square, this square, times again 3 by 2, right? So total energy will be equal to 9 by 4 NF by EF k square t square. Okay, so if we raise the temperature of the system from 0 to T, this is the change of energy. This is the total change of energy that the system is going to experience. Okay, and then what is the contribution of the specific heat? That would be simply differentiated with respect to temperature, right? Because the unit the energy required to change the temperature by 1 unit, that is the specific heat, right? So this quantity will be CVE now, and this will be equal to 9 by 2 NF by EF KB square T, right? We differentiate this, it will be 2T, 2 and 2 will go away. So this is the expression now for the electronic contribution of thermal conductivity. Okay, and one more thing that we can define is yes. So put KB TF equal to EF, or I should write the other way. Put this EF, which is the Fermi energy, we express it in terms of an temperature, okay, and this TF is called Fermi temperature. So this does not have any physical significance as such. Actually it does, but that's not important here. We are just rewriting this energy in terms of the Fermi in terms of another equivalent expression, okay, and we define a term which is called TF, the Fermi temperature. Okay, so it in a way it's the statistical temperature corresponding to the Fermi energy. That's all it is. Okay, so now if we just rewrite the entire expression, we find that the CVE is equal to 9 by 2 NF KB and then a factor of T by TF will pop out, right? So this is now the expression for CVE from the Fermi-Dirac situations. Okay, Fermi-Dirac distributions. Fermi-Dirac distributions. Now recall what was the expression for this Fermi-Dirac for the electronic contribution to specific heat that we obtained from just the Drude model. Okay, so from Drude model, this CVE, it was equal to just this factor. Actually it was 3, not 9 here. Let me just quickly confirm. Yeah, right. So but this factor of 3 will not cause an order of magnitude difference between the two expressions. So the main addition from which comes from this Fermi-Dirac distributions, it's this factor here, okay, T by TF, right? So let's see what it does. Okay, now if we are at room temperature, consider a metal at room temperature. Okay, so consider a metal at room temperature. Okay, so what does room temperature mean? It means that this temperature is 300 Kelvin. Okay, so this is 300 Kelvin. Now what is TF? Okay, how do we evaluate TF, the Fermi temperature? Right, so if we assume, or there's no assumption, for a metal with Fermi energy of uh, few electron volts. Okay, let's say 1 or 2 electron volts, right? This Fermi energy or Fermi temperature, Fermi temperature is around 10,000 Kelvin, 4 zeros. Okay, from this expression. Okay, if we consider the Fermi energy is a few electron volts, then this is a Stefan-Boltzmann constant, and this then we can evaluate, and it comes out to be around 10,000 Kelvin. And this for metals, it is the case that you cannot have more than this Fermi energy. Okay, Fermi energy is of the order of this, right? And even for a few semiconductors as well. So this is the average, or let's say the ballpark value for this Fermi temperature, right? And now if we take the ratio T by TF, right? This was 300, this was 10,000, of the order of. Okay, we are talking in order of magnitude terms. So there is a factor. So this is, let's say, 10 power 2, and this is 10 power 5. No, 10 power 4, right? So there's a factor of 100 here, which is getting divided to this expression. Okay, and if we go back to the statement that we wrote here, right? What was the goal? Our CVE was off by a factor of 100, right? From as calculated by the Drude model, right? Okay, so we see that the Drude-Sommerfeld model. Let's write it. So let's write few things down. So considering room temperature, and room temperature means T of the order of 300 kelvins. Okay, T by TF is of the order of 0.01, right? And this correction factor correctly predicts the value of CVE using Drude-Sommerfeld model. Right? So what are the takeaways now? Okay, so we have found a new model, which is the Drude-Sommerfeld model, and it correctly predicts the value of electronic contribution to thermal conductivity, and it really accounts for the correction term of 100 by a factor of 100. It corrects the value, and it shows us that where that term comes from. Okay, what's the origin of that term? But more importantly, if we look at the larger picture, what we see that is that the classical picture, which is given by the Maxwell-Boltzmann distribution, right? That is insufficient or inaccurate to predict some properties, which really shows us that the quantum mechanical picture, which is this Drude-Sommerfeld model relies on, right? It relies on the Fermi-Dirac distributions. It shows us that this quantum mechanical nature, it actually is what nature behaves like, right? So this quantum mechanics and the quantum mechanical approach, although we do not have a full intuitive understanding, of it, but still it 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 is successful, right? And other models fail. The classical model fails, but the quantum mechanical perspectives, they always, and to date, till date, they have not given an incorrect value, or they have not been challenged by experiments. Okay, all the predictions of quantum mechanics, not all of them have been verified, but whatever has been verified experimentally, it has not challenged quantum mechanics so far. Okay, so that is the bigger picture uh, from this discussion, right? So I think, yeah, that's all I want to cover in this lecture, but we can quickly have a look at some short answer questions just for clarifying the concepts. Okay, so yeah, so let's take a question. Okay, so in the quantum number space, the allowed energies and energy levels, right, form a, and the options are square, this is an easy one, sphere, hemisphere, and D is whatever, you can put none of these, right? So what is the correct option here? Anyone? Would anyone like to answer?
Sir, sphere.
Sphere. Okay, so but yeah, so this feels like the correct answer, but let's read the question again. Okay, it says that in the quantum number space, the allowed energy levels form a, right? So it doesn't necessarily have to be a sphere, right? Because it is the energy levels. So what forms the sphere? Okay, if we recall that expression, we have nx square plus ny square plus nz square equal to constant, right? And this is for a constant energy. Okay, so unless it is given that your energy is constant, then we cannot say that this forms a sphere. Okay, so maybe in the question we should somewhere it should be included that the energy levels should be constant. Okay, or iso energy surfaces, those are spheres. Okay, now that's point one. Now I'm just discussing this question. If you want, you can mark this as a sphere as the correct option, but there are some things that should be taken care of. Okay, I'm just copying this example from a textbook, uh, which also in that textbook sphere is given as the right answer, but we should take care that of the concept. Okay, the energy should be constant for us to conclude that this is a sphere. Okay, and I don't see in this problem the word constant or iso energy written somewhere. So that's one point that we should take care of. The second point is it will never be a full sphere, right? Because for a sphere, these quantities have to be negative as well, right? So at best, it will define 1/8 of a sphere, or what's called an octet. Octet? No, maybe not octet. So 1/8 octant probably. Quadrant, and then we have octants in 3D. Yeah. Octant of a sphere. Okay. Because nx, ny, nz, these all must be greater than 0. Greater than 0, yeah. Right? So it never describes a full sphere. It will at best describe 1/8 of a sphere, and that too if the energy levels are constant. Okay, so these two things we should take care of, and then we can say that the sphere is the correct option. Okay, so let's take one more. So I am choosing only the conceptual problems because these are important, or I feel they are important, more important than the calculations. Okay, Fermi energy of metals. Is the same for all metals. B will vary from metal to metal. C changes with temperature. And D is highest at room temperature. So what is the correct option for this one? Any thoughts? So which of these statements is true for Fermi energy? So is it same for all metals? Is the Fermi energy same for all metals? What about if we take sodium and calcium? Will it have the same Fermi energy? So no, right? It will not have the same energy. The Fermi energy changes because the Fermi energy, first it will depend on the number of electrons present in the system, right? Because the more electrons you fill, you are going to fill higher and higher energy states. So no, it will not be same for all metals. Okay, and a heavier metal we mean the number which has more number of electrons, it will have higher Fermi energy in general. Okay, so this is wrong. The second option is actually correct because it will vary from metal to metal. If it's not the same for all metals, so it follows from one. And third thing is it changes with temperature. Okay, so first of all, Fermi energy is defined at zero temperature. Okay, that is the Fermi energy. And for all other temperatures, it is defined as as the where the probability of occupancy is half. Okay, so I don't think that this is the correct option either. And the fourth one, it's highest at room temperature. That is also wrong. There is nothing particular about room temperature that will make it the highest. Okay, so the option B there is the correct one. And we can take one last conceptual problem. Right. So let's take something which is, yes, so this is a good problem, that when temperature is increased, okay, so as per the Drude-Sommerfeld model, as per Drude-Sommerfeld model, which of the following is true? Okay, option A, electrons within kBt of Fermi energy can participate in the process of energy increase. Number B, the same thing, but instead of Fermi energy, it says electrons within kBt of zero energy. Okay, and option C is that all electrons can participate in the process of energy increase. And option D, no electron can participate in the process of energy increase. So which of these is true? Okay, so it asks us to uh, basically what is the correct option, what happens if we consider Drude-Sommerfeld model and we allow the temperature to increase. So first of all, what about option B? Is option B true? Or okay, let's look at option D, that no electron can participate in the process of energy increase. Does it seem it's true? Right? So this option, we can directly say that it's not true, right? Because if no electron participates in the process of energy increase, then energy will not increase. So what it means is that when temperature is increased, the energy does not increase, which contradicts the first law of thermodynamics, right? So this is false. Let's look at option C, that all the electrons can participate in the process of energy increase. Now this is again false, because we have seen that this happens in Maxwell-Boltzmann statistics, not the Fermi-Dirac statistics, because the Drude-Sommerfeld model, it's based on Fermi-Dirac and not the Maxwell-Boltzmann. So this is also wrong. Now it's between option A and B. So A says that the electrons within kBT of Fermi energy takes place in the process of energy increase, and option B says that electrons within the kBT of zero energy takes place in the process of energy increase. So let's go back to this distribution and see what it means. Okay, so this is what it means. So option A says that these energy levels which are in kBT of the Fermi energy, they take place in the energy transfer process, and option B says the energy states which are here, they take place in the process of energy transfer. So this is, we know that this cannot happen, right? Because if a jump of kBT is to happen here, it will take the electrons to maximum here, right? Somewhere here. From here, a jump of kBT happens, then the electrons will reach here. But we know that these states are already filled, right? These states are already filled because of this distribution. We know what the distribution looks like. Okay, these states are already filled. So nothing, no jump here. So if these electrons have to be excited, the jump has to be so huge, right? It should be at least this huge. So and many of times the jump required here, it would be so large that we cannot even create that kind of energy practically, okay, inside a laboratory. So these electrons will not in general react to the temperature field that is applied. So when we change the temperature, it's only the electrons within the kBT of the Fermi energy, because they can jump easily and these states are unoccupied, so they can occupy the next available states. But these, they will require a much larger jump, right? So the correct option for this problem is option. So this is also wrong, and the correct option is option A. Okay, so if there are any questions, please ask. Otherwise we can conclude here for today. Are there any questions?
No, sir. Thank you.
Okay, thank you so much. So we will meet. I'll upload a video sometime this week for the missed lecture, and then we will have our regular TA session on next Saturday, 6 p.m. Okay, so thank you everyone.